And then we will create a new model, that is DNN model we are creating. That this is a local variable where we will store the model. From Keras, in Keras there are two types of models available. One is sequential model and one is functional API model. Sequential models takes input in the form of, it can take only single input and generate single output. And here you can process the data in sequential format. If you want to create a model with multiple input or multiple output, then you can go ahead with the functional API example. So currently we are using sequential model. Functional API also we will do, maybe in upcoming labs. So from Keras, there is models available here. From here, if you want to use sequential, you have to write sequential. If you want to use functional, you have to write model. So sequential. So it will call the sequential model. Then to add the layers in the model, there is a function that is add, which will help you to add multiple layers in the model. So there are multiple ways to creating the model in TensorFlow or Keras. If you find that this is the other ways other than this way, so that is also correct. In this lab, we will follow this particular way to creating the model. In upcoming labs, we will change the syntax so that you will learn how are the ways to create the model. So ANN_model.add. This is the way you will add the layers. One of the way. So as explained by Sir, in artificial neural networks, the first layer is input layer. Then it is followed by single or multiple hidden layers. And then at the end, you will have output layer. So we are creating the first hidden layer. That also using the same Keras dot layers dot dense. So dense is the type of layer which creates, which is helpful to develop artificial neural network. So why dense? Dense is densely connected neural network because all the neurons of the first layer is connected to all the neurons of the upcoming layer. So that's why dense is the layer. So as you can see, it is giving the suggestion. Dense takes multiple parameters as input. You can see the units or number of neurons, the activation function you want to use, whether you want to use bias or not. By default, it is true. You can see it is showing here. The kernel initializer. So somebody was asking in the first session that how you can initialize the weights. So this is the parameter you can pass. Kernel_initializer is equal to, this is Glorot uniform. You can use normal or the random normal distribution of the weights. So there are multiple options available in the Keras websites to initialize the kernel or weights. You can use those weight initializers. Then bias initializer. In many of the applications, I've seen that the biases are initialized with zeros, and then you can, there are other ways also. Then the regularizer you have understood in the first session, that also you can initialize from here, L1, L2, or similarly with the bias regularizer. And other options are there that generally we don't set. So let's go ahead. Now the next thing is the number of units in the first hidden layer. That is a hyperparameter because user have to set how many parameters will be there. Here we generally follow the rule that it should be in power of 2. and it is 2n plus 1 way. So it also depends on your application, as well as you have to try with multiple combination that which works best in your application. So in the first hidden layer, I'm using 16 units or neurons. I'm taking it small so that I can explain you how to calculate number of parameters and output shape. Next is you have to pass the input shape to the first hidden layer, only to the first hidden layer. So the parameter is input shape we have to pass. So let me check what is the shape. When you have reshaped, you know this is 36 cross this number 150528. So 36 images are there, means one sample is of size 150528. So the number of neurons in input will be 150528. 150,000 and 5,200 neurons will be there. I'm writing comma here because it is one-dimensional shape, so I have to write comma. Then you can initialize the kernel or weights by using Kernel Initializer function. Let's set the default one is Glorot. So we are using normal, so random, normal. Let's and the other one is he distribution. That sir was explaining. That also we can use. Then bias initializer. So let's initialize it with 0. Then so this is your first hidden layer. Again, we will add one more layer with 32 and we will use the same initializer, and here no need to use the input shape parameter because we have already given the shape for input layer in the first hidden layer. So only kernel initializer and bias initializers we will use here. And now let's create the output layer for now. Later on we will change the structure, but for now let's create a neural network with two hidden layers. One is with 16 neurons and one is with 32 neurons. So model.add Keras.layers. We have two classes. One is good and one is crack. So good is represented by 0 and crack is represented by 1 when we have pre-processed the data. So we will use 2 neurons in the output layer. If you have 10 classes, you have to use 10 neurons in the output layer. If you have 100 classes, accordingly, you have to change the number of units or number of neurons in the output layer. Function as well. You have two very hidden layers also that we will do while fine-tuning the network. We will update the number of the number of neurons and activation function. So in the output, you can use sigmoid or both are different activation functions the sigmoid gives you the output in between 0 to 1 for each the neuron. And in softmax, it will give you the probability value that will be also be in between 0 to 1. But here the softmax generally we use for classification, only for classification purpose. So I think that's all let's now run it. And now we will take the summary of the model. So this is we will know how it is printing, but I request you all to kindly do the same in your system. We will wait for 2 minutes so that you can run the same code. If you are getting any type of error or any issue, please report it in the chat box. This is the most important part of the DNN model.
So Saida is asking, Saida Shira Moin is asking, since we have just 2 classes binary classification, why can't we use just one neuron in the output layer?
That also we can do. We can use one, and here we can change the like activation function. Both is possible, but it's a like it's not. We can say that we are working with single class. We are working with 2 classes, so that we are following this standard, not using the one class in the output layer. Shape depends on, let me explain you again. What is the shape of your single sample? Suppose your data has a single image of size 10 cross 10, then your input shape will be 100. If your image is of size 10 cross 10 cross 3, that is RGB image, then your input shape will be over here. Input shape is the shape of single sample or single input, single image. In case if you in this example we have image of size 224 cross 224 cross 3, that's why input shape is this 150528, because artificial neural network takes your input in one dimension. So each image will be converted to one dimensional image. So can you please paste your error, whatever error you are getting, if you will paste, then it will be easier. Yes, we can use one. Here you can use one neuron, and here you can use the activation function in place of softmax. You can use sigmoid and convert it in a binary classification. That is also possible. Both the ways you will, your neural network will be work well. And I request you all to please write the complete code in a single cell. If you will create multiple cells, then there are chances that you will encounter this error. Input shape is not accessible in all the layers, and then you may have more than 2 hidden layers in your network. So this kernel initializer or bias initializer initialize the weights and biases because somebody was asking in the first session that how we can initialize the weights fixed or particular numbers in place of randomly initializing. So here in place of random normal, you can also give the fixed values or any other type of distribution. So if you are done, please report it so that we can go ahead. So you can use softmax for multi-class classification. Sigmoid also you can use here. So these are hyperparameters, 16, 32, and 2. These are hyperparameters because these depends on the developer or whosoever is developing these neural network. So Relu activation function generally we use in hidden layers, not in the output layer. We use Relu activation function in the hidden layers. Now let me explain this model and then we will go ahead and whatever queries you will have, we will one by one answer. So input is this 150 cross 150528 neurons. In the first hidden layer, you have 16 neurons. So here, when you visualize, let me try to annotate. So suppose this is your input layer. Suppose which will have some, sorry for my writing, suppose it will have some 10 neurons in it. And this is your first hidden layer which have 16 neurons which we have taken currently. Then all the neurons of your input, all the input neurons will be connected to first hidden layer, like in this manner, that is densely connected. Then in the second hidden layer, we have in the same way, your neurons will be connected from one neuron or multiple neurons. So in this case, I have selected 2 neurons. So here you will see the connection will be, each neuron is connected here with 16 neurons. So we have 10 neurons in the first hidden layer and here we have 16 neurons. So number of or your weight matrix will be of size 10 cross 16 for the first hidden layer. And number of biases here will be 16. For each neuron, you will have a single bias. Similarly, when you talk about second hidden layer, here each neuron of first hidden layer will be connected to all the neurons of second hidden layer. So here the weight matrix will be of size 16 cross 32. And for each neuron you will have a bias. So total number of biases will be 32. Here also each neuron of second hidden layer will be connected to all the neurons of output layer. So the weight matrix will be of size 32 cross 2 and each neuron will have one bias. So there will be two biases in the output layer. So in the entire network, the number of parameters represents the size of weight matrix for an size of weight matrix in each hidden layer sum up with number of biases in all the hidden layers. So here the weight matrix will be of size 10 cross 16. Number of biases will be 16, so plus 10. Then 16 cross 32 plus 32. 32 cross 2. That plus 2 will be the number of parameters here. So here in this example, in the first the number of the size of weight matrix will be 150528 cross 16 plus 16. So this much of the number of parameters will be there in the first hidden layer. In the second hidden layer we have 32 neurons. So the weight matrix will be size 16 cross 32. 16 cross 32 plus 32 will be the number of parameters here. That is 544. 16 cross 32 plus 32. In the output layer, 32 cross 2 plus 2. That is 60. Parameters will be there. Trainable parameters will be there in the model. This is the way you will calculate the number of parameters in your model. And these are the parameters, weights and biases that will get learned in your backpropagation process. So let's go ahead with model training. Before training, you have to set some more hyperparameters. That is the optimizer you will use, the learning rate in the optimizer, what is the loss function you are using, and the matrix you are going to use to evaluate the performance. So let's use both. First of all, let's use SGD optimizer and then we will change it. So to access the optimizer, in the Keras itself, we have all the optimizers available. Keras.optimizers.sgd, and here we will set the learning rate. So learning rate generally we set in between 0.0001 to 0.1 and or 0.0005 to 0.5. So it is again hyperparameter. So you have to try with different learning rate. When you plot the training graph, then you will understand whether the learning rate should be changed or not. So here we are setting it as 0.0001. This is the optimizer we are going to use. Next, we have to pass this optimizer to your ANN model. That we will do using compile function that will compile your model with the optimizer, loss function, and the matrix you are using, accuracy, precision, recall, other things. So optimizer, we will pass. You can see the default one is RMS drop. We will use our optimizer, that is optim. the loss function you want to use. So the loss function is cross entropy loss we will use. Here, your data is in the format that is 0 or 1. So we have to use sparse categorical cross entropy loss, and we are using softmix here. Or categorical. And then we will use matrix. The matrix you can use accuracy, precision, recall, whatever you want. So currently we are using, I'm writing sparse here because I'm not converting the what we can see, the output vector into one hot encoding. That also we have to explain that what is one hot encoding. So that maybe in the tomorrow's lab we will explain. So that's all for compilation. Optim is not defined. It is here. Notice. Okay, there is some syntax above O, so that is causing the error. After that, for training, we have fit function. So DNN model dot fit. Here you have to pass a train. Then Y train. Other than these two parameters, we have to pass number of epochs. Let's set it as 30. And then the batch size, how much images you want to process at once. So we are setting batch size as 4 currently. And let's store the output of this fit function in a local variable history. So you can see the performance is changing. So I request you all to kindly do the same. When you are done till the training part, please report so that we can proceed further. So, Neha ma'am, kindly check. I think X is in capital. So maybe it is because of that you are getting error. Next is the prediction part. If you are getting the error is non-time object. Because all other things are correct in your case, maybe your session has expired, so DNN model you have to rerun the code from here. Next is identifying the matrix on unknown or test dataset. So for that, two separate functions are there. For matrix identification, we have evaluate function, and on predicting on unknown dataset, we have predict function. So one by one, we will see. To get the performance on test dataset, we have DNN model. First of all, call the model, then dot evaluate, and here you have to pass x underscore test comma y underscore test and run it. So you can see the loss is 0.73 and accuracy is 50%. In your case, it can be different. So this is on unknown data or test data set. To predict on unknown dataset where we don't have labels or this Y test, you have to call predict function. Here 0.5 means this is this one accuracy, it is printing it as 0.5. So you have to use ANN model dot predict to predict on unknown dataset where you don't have label. So now again, if you want to use the same matrix to calculate, let's print y predict. Here you can see 0.43 and 0.5. So it is giving the probabilities for different like probability for each image. The probability of being in class 0 is 0.43 and here it is 0.56. So what you have to do, you have to use argmax. So y predict is y predict dot argmax. Sorry, we have to use numpy np dot argmax over y predict. Axis we will set as 1. So it will give us the maximum of. So you can see this is the prediction it is giving us, and the actual one we have in y test. So this is the way it is predicting. Your model is trained for, and it is giving 50%. That means 50% it is incorrectly classifying. So this can be because of less number of data, it is not trained properly.
So what is, can you compare the performance of two classifiers?
So ma'am, many of them is getting this 64.28. In my case, I'm getting 35.71, and here I'm getting 50%. So maybe they are getting here also, they can get 60s and 72, up to 72.
No, by this I mean,
Like we have to change here the
Scroll down, scroll up. Okay. So is that all? I think it's already 7:52.
Yes, ma'am. So if anyone has,
So we can ask participants to, like Darshan has raised his hand. Darshan, can you?
Hello, madam. I'm audible, madam.
yes, sir.
Sir, madam, that the parameter value is reduced, madam, from which number to from 66.
Pardon, sir. Parameter values.
There, madam, in the DNN model, madam. Little bit upwards. Little bit. Here, madam. Here. Down, madam. In the summary, madam. DNN dot summary. So here parameter is just 240, some number is there. Finally, it has gone to 66 in the third column.
Third column 66. No, okay, sir. Yes.
Is there any formula to how to calculate the trainable parameter?
Yes, sir. That formula is number of neurons in the first layer followed multiply by number of neurons in the next layer. For example, the 66 we are getting because your output layer has 2 neurons and it is connected with the previous layer is with 32 neurons. The number of parameters will be 32 cross 2, that is your weight matrix size. 32 cross 2, that is 64. Your weight matrix will be of size 32 cross 2. And for each neuron here, you will have one bias. So 2 biases will be here. So that's why we are getting 66.
Okay.
Similarly, here also 16 cross 32 will be weight matrix. And for each neuron, one bias. So total 32 bias. 16 cross 32 plus 2. Same with first. 150528 multiply by 16 plus 16.
Thank you so much, madam.
Thank you, sir.
So Pankaj Kumar, will you please ask your question?
Hello, ma'am. Hello.
Yeah.
Okay. Ma'am, I have two questions. First is related to this number of layers and number of neurons we are selected in this case. So if we change the number of layers, like we can increase, we can add on more layers, or we can add more neurons on a single layer and can reduce one layer. So how it impact the process? Will it impact directly to the result? Our model will performance will increase or decrease, or it will impact on the timeline, how long this process execute to get the result. First question is this, ma'am.
So can I answer this question, Puna?
Yes, ma'am.
See, the deeper is the network, the more abstraction it learns from the data, right?
Okay.
So if the data is not very, if your data is having, your data characteristic is, the data features are such that they are not very complicated, not very difficult from the point of view of understanding its features, then less number of layers would do. If you want to get the work done from just one single layer, there are some machines which are known as extreme learning machines. They use only one layer.
Okay.
Now they are doing also very well in many cases, but deeper is the network, higher is the probability that it will learn the characteristics of the data in a more abstract way. So once we say that it is an abstraction, it learns in abstraction, it basically is able to generalize well. That's the idea. So generalize well is what precisely is expected from a learning model.
Okay, ma'am.
Yeah, so, but if you have more neurons, some of them will be learning redundantly. They will be learning the same features or same extracting same features, and there can be some redundancies. But it is always preferable to have redundancies than to lose the information. Therefore, people choose a lot of neurons in each layer.
Okay, ma'am. So, like, while choosing the number of neurons, like, how do we decide? We just see the
It's hyperparameters are generally tuned. They are first by trial and error, by previous knowledge.
Okay.
You do that, and then by trial and error, they are tuned.
Okay,
There's
ma'am.
no hard and fast rule, but as Dr. Partha Pratyam said, that there are certain theoretical results which say, for example, if the input data feature is having size of say 4 or 40, then you can take the number of neurons to be 80 plus 1, like 2n plus 1. For a data sample with having n features, 2n plus 1 can number of neurons in the first hidden layer can do very well. But again, these are theoretical results which have been further improved. But in practical cases, it's difficult to.
Okay, ma'am. Thank you so much. Ma'am, can you just scroll down to the bottom side? I have a question. Okay, the question is, ma'am, on the ANN at the end, like.
Okay, we are at the end only.
Yes, ma'am. Okay, so here are two statements. One is the evaluation, and second is the prediction. So, what I understood from these two different statements, the evaluation is just a kind of summary, and the prediction is actually for producing the result. Is it correct, or like why we like executing two different lines to get the output?
Here you can see that we have the labels with us. We have the output in which class or category your data belongs.
Okay.
But when your model is ready completely,
Okay.
you have to test it on real-time data where you don't know from which category the data belongs.
Okay.
In that case, for real-time prediction, you use this predict function where you don't have the label.
Okay. So here. Okay, both are different.
Yes.
Okay,
Yeah,
ma'am.
so your model is ready. Basically, your model is evaluation is the performance evaluation of your algorithm. And
Okay.
testing means you are testing for an unknown sample. Okay. Shall we move to the next person? Shyam Bahadur, I am asking Shyam Bahadurji, I am asking you to unmute.
Okay, good evening, ma'am.
Yeah, good evening.
Hello. Yes, ma'am. My question is, if we increase the number of epochs, will the accuracy of the system will increase?
Number of neurons, what did he say?
No, ma'am, number of epochs.
Epochs. The number of epochs basically, say, you suppose you have a child, right? The child is very bright. If you tell him 3 examples, the 4th example he will learn automatically. I'm talking about mathematics, right? The child is not good in mathematics. He may be very bright in other areas, but not good in mathematics. Give him 15 examples. He will learn slow, and his performance may not improve with that, even with 15 examples. So, similarly, machine learning algorithms are also like that the number of epochs, after certain number of epochs, they may not learn further because they have already exhausted from the data set. They have learned whatever they could learn. Beyond that, what happens that the error tends to it may start increasing also. Have I answered your question? So I go to the next person, Pranamita Nanda. Yeah.
Yes, ma'am. Good evening, ma'am.
Good evening.
Ma'am, my doubt is whether for the same hyperparameters, is it possible to get different accuracies? If so, why?
Because your weights actually are randomized, like initial, you do not know what is the starting point, right? The moment you randomize your weight, the starting point can be very close to a global minimum. It can be very far from a global minimum or a local minimum even. So the accuracies may change. The performance may not be the same. May not be the same always.
Okay.
Is that clear?
Okay, ma'am. Then how to know? Just one more. If suppose one time I am getting suppose 50%, next time I am getting 70%, then how do I know for what? That means whether I have to change the hyperparameters or is it because of weight it is.
So you slowly have to change the hyperparameter. Then only like take one hyperparameter, slowly change its values, and then you understand. Like it's a problem of research in itself. So there's no hard and fast rule, as we said.
Okay, ma'am. Thank you.
Thank you. So I'm requesting Manojit to please mute his. Is Manojit available? No, I don't think he was present. All right, Femina, request you to please unmute yourself.
Thank you, ma'am. This as we increase the hidden layers, will we get more accuracy? I mean, how do I balance that? Deciding the hidden layers.
As I just told, that hidden layers help you learn the data abstraction features at different abstraction level, right? So it depends on the data. It depends on the application from where the data is coming. Then the more hidden layers. And the second thing is that the deeper is the network, it requires more data to train itself. If you have a small number of data, if you have only 200, 300 samples, then 2-3 hidden layers are sufficient. If you have some, say 5,000, 10,000 samples, you can take up to 7, 8, 10 layers. Some people even take up to 50 layers. So we'll be talking more about that in a transfer learning session later. Okay, thank you. So now I request Manojit, please, unmute yourself.
Good evening, ma'am.
Good evening.
Ma'am, actually, I have one question that I have a image feature like 1 lakh image feature. Can I directly apply this image feature in this ENN?
You have an image feature if your sample is of size 1 lakh. Then definitely neural networks are known as feature extractors. You can apply. Your neural network will be very large. And what kind of feature is this? By the way, it's a temporal data or it's a spatial data? Is it a temporal data or a spatial data?
Ma'am, it is a spatial data. If
it is a spatial data, then you will learn tomorrow. My colleague, Dr. Professor P.K. Khanna is going to deliver a lecture on convolutional neural network in place of me because of some exigency. I'm not taking. She will be taking the lecture. So you will learn more about temporal spatial data tomorrow.
Okay, ma'am. Is there any transfer learning concept we are going to use in our coming session? But I want to know that shall we use this transfer learning feature
Unless you
in
know,
our
unless you learn what is CNN, transfer learning will not be of any use. So we will be doing transfer learning in a later
ma'am.
session. First you will
Okay,
learn
ma'am.
CNN and then transfer learning also.
Yes, ma'am. Thank you, ma'am.
Saida ji, request you to please unmute yourself.
Yes, thank you, ma'am. Good evening. Am I audible?
Yes.
Yes, ma'am. Ma'am, actually, I was wondering the DNN model that Purnima ma'am designed in this session, she didn't specify the activation functions for the hidden layers. So I was wondering without having activation function, those hidden layers won't be just computing some linear function based on the weights and biases. So would that be meaningful? I mean, activation functions help in introducing that non-linearity thing and learning the complex
Purnima?
features.
Yeah. Purnima, are you there?
Yes, ma'am.
Yeah.
Yes,
Have
ma'am.
you not taken any activation function?
No, ma'am. Initially, I have not taken. I want to one by one want to add the parameters in the function.
Yeah.
Okay, so you
So
would be adding
basically, if you don't take any activation function, it will be a linear, like affine approximation. But if you take an activation function at the end, it will introduce non-linearity at the end only. So this was just to help you understand how things are growing. But you can take activation function for sure. I mean, generally, it's a practice that activation functions are taken. Okay. Thank you. Next is some Vaishali and somebody raised hand. I don't know Vaishali. I don't know if she was the person who raised. Vaishali, are you there? Vaishali ma'am, you were asking some question? All right, so there are no further questions and we wish you a very good evening. Thank you so much, all the participants, for your active participation. And we will be meeting tomorrow at 2:30. Professor Preeti Khanna will be taking a lecture on, delivering a lecture on convolutional neural network in my place. And request you to please join before 2:30. That's all. Have a nice evening, all of you. Enjoy your dinner and good night later. Thank you.
Thank you.